Hi everybody, welcome to lab number 8 of GG497 Geological Visualization. In this lab we're going to have two separate structural contour exercises about unconformities and faults. And the first lab, it asks you to use map 8A and answer a set of questions and draw a schematic cross-section based on this map, map 8A, which shows an unconformable surface between two packages of sediments. And then the second map, map B, has map 8B has a fault which has displaced a series of conformable rocks, and from that map need to ask you some questions about the direction, the geometry of the fault, the sense of displacement, and so on. Okay, well, let's get started then. For question number 1, it asks you pretty straightforward, can you recognize where the unconformity is? And if we look at the contacts between the coal seam that's labeled, if we follow that coal seam up and around the area, you can see that it disappears or is truncated by the contact with the blue unit. So if we follow the coal seam, we can follow it this way, this way, this way. You can still follow it in outcrop, and then it stops, it gets truncated, it disappears beneath this unconformable blue unit, and then it reappears back where we expect it in its own sedimentary package. So this unconformity is pretty straightforward to label. It's basically that blue, the basal contact of that blue unit. It truncates all of the other contacts in the other older sedimentary rock package. The next question asks us to find the points where we know the height of the unconformity, and to do this, or we can use these to then work out the structural contours, okay, to show how that unconformable surface is dipping. So we need to find all of the places where we know the height of the unconformity, so where that unconformity crosses one of our topographic lines, topographic contours. And if I mark on all of those points, we get it in those 6 locations. Then, just as we've done in previous exercises, if we join up those points of equal height, so for instance here the unconformity hits the 900 and it does here it hits the 800 and here it hits the 700 and there, we can connect these points and extend them to give us our structural contour set for our unconformity. If we wanted to, we could extrapolate these to include the 1000 line, but in our map we barely reach 1000 meters elevation. It's just this tiny bit, so I'm not going to bother, otherwise it will make the map look far too cluttered. Okay, so that's that question done. We've got our structural contour lines for our unconformity. The next question asks us to find the strike dip and dip direction of the unconformity, and then to mark the dip of this unconformity in the beds above the unconformity with an appropriate symbol. Well, we need to first of all figure out the scale of the map, and when we get our ruler up to the scale bar, we see that 25 millimeters on the map is equal to 250 meters in real life. So therefore 1 millimeter on the map, we take that 250, we divide it by 25, and it tells us that 1 millimeter on the map is equal to 10 meters in real life. So then to measure the dip, we need 2 points along the unconformity where we know the height of the plane. And between these 2 points in the dip direction perpendicular to the structural contours, we can see here the height of the unconformity is 900 and here it's at 700. So there's this 200 meter change over this horizontal distance. So measuring that horizontal distance between those 2 points, we see that it is 113 millimeters. And if 1 millimeter is equal to 10 meters, we take that 113, multiply it by 10, and it tells us that that distance is 1,130 meters in real life. Okay, so now we've got our 2 points along the plane, and we know the height change is 200 meters between those points, and we know that height change occurs over 1,130 meters in horizontal distance. So now we can build ourselves a conceptual triangle, and to calculate the dip of that unconformity, we take the inverse tangent of the opposite divided by the adjacent. So we take the inverse tangent of 200 divided by 1130, and that tells us that the unconformity and the rocks deposited above the unconformity are dipping at 10 degrees. So we mark that on the symbol on the map using the appropriate symbol, keeping our strike parallel to the structural contours. The diptych points from high to low, and then the number that we record is the amount of dip, that angle that we've just calculated. Okay, next it's asking us to draw and label with heights a set of structure contours for the coal seam. So again, just like we did, we find all of the points along the coal seam where we know the height of it, so wherever that coal seam crosses a topographic contour. And we mark all of those on like so, and then we got some on the other side. Yeah, that's all of the places. And then just like we did with the other set of structural contours for the unconformity, we connect the points of equal height to show the structural contours, and we've given them the labels, and we can see all the way across the map that they've got a nice equal spacing, indicates that it's a uniformly dipping coal seam. And now, again, just so we get some good practice at it, the next question is asking to calculate the strike dip and dip direction for the coal seam, and to record this appropriately. So again, what we do is take 2 points along that plane of that coal seam that we know the height. So let's say here and here we know it's at 900, we know it's at 500 meters height there. We measure that distance between them, and that comes to 104 millimeters. We've already done the map scale. We know that 1 millimeter equals 10 meters in real life. So what we do is multiply that 104 millimeters between our 2 points by 10, and it tells us that distance is 1040 meters. So that 400 meter change in elevation of the coal seam is occurring over a horizontal distance of 1040 meters. So once we've done our measurements, we can use our trigonometry to calculate the amount of dip. So our 400 meter vertical change is occurring over 1040 meters horizontal distance. So the amount of dip of our coal seam is the inverse tangent of opposite over adjacent. In other words, our inverse tangent of 400 over 1040 tells us that the coal seam and that package of rocks which it is in is dipping at 21 degrees. So then we whack on our symbol. I've actually somehow managed to put that symbol in slightly the wrong place, but if we moved it over to the coal seam, it would be the strike line would be parallel to the structural contours, and it would be dipping, the diptych would be pointing from high to low with the number recording the amount of dip. Okay, but that symbol, somehow PowerPoint has moved it upwards. It should be close to where we've measured, so it should be on the coal seam somewhere. Okay, then this next question is asking us on the map to mark the subcrop of the coal seam immediately beneath the unconformity. Or in other words, mark on the map the position the coal would be if you could remove the rocks deposited on top of the unconformity. Okay, if we think about this, where the coal seam crops out on the surface is where the height of the coal seam equals the ground surface, right? So wherever we see this coal seam, we see it there because the height of the coal seam is equal to the height of the ground. That's a very obvious thing to say, but just need to understand like what the ramifications of that are. So if the coal seam's position on the ground is where the height of the coal seam equals the height of the ground, then by the same logic, the coal seam would crop out underneath the unconformity wherever the height of the coal seam is the same as the height of the unconformity. So what we can do to find all of those points where the height of the coal seam is the same as the height of the unconformity, we can overlay our two structural contour maps. These are our structural contours for the coal seam, and these are our structural contours for the unconformity. So wherever those two things are the same, that's where the unconformity and the coal seam would intersect. Okay, so now what we need to do is mark on all of the points where the height of the coal seam contours and the height of the unconformity contours are the same, and where both are still beneath the height of the ground. If they were above the height of the ground, then that means that they've been eroded away, so we won't see it anyway. So we need to find it where they're equal and both below the height of the ground. Okay, so here they're both at 900, and the ground is somewhere between 900 and 1,000 meters high, so that would be one. Here they're both at 800, and the height of the ground is somewhere between 800 and 900, so that would both work. Here, both sets of contours are at 700, but the height of the ground is somewhere between 600 and 700, so it wouldn't exist there. It's been eroded away from that point. Okay, so those 2 points would be where, if we could scrape off the unconformity, that's where the coal seam would crop out. So we can interpret the run of the coal seam between its surface exposures where we can see it and where it would be beneath this unconformity. So we can join up those 2 points, and then we can join up with the other exposure on the surface. Okay, this next question, I need to get our resource extraction heads on, I guess. This question is now asking us, on the map, shade all areas where the coal is present below the ground at a depth of less than 100 meters. So imagine the company is trying to extract this coal, and they can only make it economically possible if they only have to remove a maximum of 100 meters worth of rock. Okay, so what we need to do is find all of the points where the height of the ground, or the difference between the height of the ground and the height of the coal seam, is less than 100 meters. Okay, so all of those points where the height of the ground is 100 meters or less than the height of the coal. Okay, so here the height of the ground is at 1,000 and the height of the coal seam is at 900, so that's one. Here the height of the ground, if we follow the contour, is at 900 and the height of the coal is 800. Here the height of the ground, if we follow this contour around, it's 800 and the height of the coal is at 700. And we continue that process and find all of the points that satisfy that condition. Okay, the other set of points are where the height of the ground equals the height of the coal. And so in between those points, that condition is satisfied. So between these 2 points, the height of the coal is present at a depth of 100 meters or less. Okay, that might take a little bit of visualization, but if you can follow the maths behind that, then you should be able to come up with something similar as an interpretation of where the coal seam can be extracted from. Okay, so then it's asking us to construct a cross section along the line XY in the space below. So as ever, we take our strip of paper and we line it up between our boundings and we mark on the ground heights that we cross. So this is quite a simple hill profile to do between X and Y, and we mark on the 3 ground heights that we cross. Okay, then what we do is mark on the rocks that we see at the surface with the thin veneer along our strip. And then what we do is mark on the intersection for the structural contours for the 2 features. So I'll first of all mark on all of the structural contours for the coal seam, and then I'll mark on all of the structural contours for the unconformity. You can see my structural contours for the coal seam are in red, and my structural contours for the unconformity are in green. So I've marked on everywhere where our cross section crosses those. Okay, then that's all of the information I can take from the map. So I move over to my cross section, and I first of all draw my hill profile by moving the heights of the contours that I crossed along the section line onto my cross section panel, and then I interpret the hill profile without crossing any of the other cardinal contour lines, because I didn't do them when I put my strip against the map. And by interpreting that, I've made myself a hill profile. And then what I can do is transfer from my strip onto this hill profile the locations where we cross a lithological boundary, and then add in a thin veneer on the top to show what the rock types would be on the surface. Okay, next thing I can do is transfer from my strip onto the cross-section panel the structural contours for the youngest feature. And the youngest feature that we've got is the unconformity, because the coal seam and the rocks that the coal seam are in, they must have already been there in order to be eroded to form an unconformity. So I plot the structural contours for the unconformity first. So I go across from where I've crossed the 800 meter for the structural contour for the unconformity, and I plot that at 800. I do for the same for the one at 900. I join them together and interpret where they go in the prior to modern day erosion, and I've produced my unconformity for my cross-section line for the unconformity. Then what I do is plot the structural contours for the older feature, which in our case is the coal seam, and I plot their structural contours at the correct heights on my cross-section panel. And then I join them up and then stop at the unconformity, because the coal seam is older than that unconformity, so when it gets to it, it's going to stop. It has been eroded in order to deposit the rocks on top of the unconformity. Then what I can do is complete my cross section. I'm free to refer back to the map to see which colors I should use. But in so doing, we should finish our cross section, and it should look a little bit something like that. We can add in labels for the coal seam and the unconformity, but I've opted for a difference in color to show the unconformity in green. Okay, so that's the first part of the lab done. Feel free to go back through the video as much as you need to get through it. Then as we move on to the second half of the lab, onto this map 8B, the first question is very straightforward, and it asks you to label the fault. Now you can see where the fault has truncated the contacts and has displaced them. So there's these green rocks that have been cut off, and here they are again. So these stratigraphic boundaries have been cut. It's not an unconformable surface. This is a faulted one. So that line of truncation marks the fault plane on the surface. Okay, then the next question asks you to draw and label with heights a set of structure contours for the surface of the fault. So again, to draw structural contours, we find all of the points where we know the height of the fault from where it crosses the structural contours. And then we join these points of equal height with a straight line which denotes our structural contour. So here and here, the fault crosses the 1100 meter ground contour. Here and here it crosses the 1000, and then here, and that's it, crosses the 900. Here it crosses the 800 and the 800, and there it crosses the 700. So I mark those on and join them with my structural contours. Okay, just by looking at these structural contours, you can tell that this feature is pretty steep. Look how closely spaced they are. And you can tell already the direction of dip and the direction of strike. Okay, so now we're asked to find the strike, the dip, and the dip direction of the fault. And what we know already is that strike is parallel to the structural contours, and it's measured as a bearing clockwise from north. So what we can do is align a north arrow to our structural contours. We can count clockwise around from north until we intersect our structural contours, and we see that those structural contours have an alignment parallel to 175. So that's the strike. The dip direction is measured perpendicular to the structural contours. So if we draw a line that's perpendicular to the structural contours and we align that one to north, then again what we can do is count clockwise from the north arrow until we hit our dip direction, and that tells us that the bearing of the dip direction is 085. So we've got our strike and our dip direction, but now in order to find the dip, we first of all need to find the scale, and our scale, it looks the same as the last map, where 25 millimeters on the map is equal to 250 meters in real life. Therefore 1 millimeter on the map is equal to 10 meters in real life. Okay, so then in order to measure the amount of dip along that fault plane, we take 2 points where we know the height on it. I've taken the 2 furthest ones I've got, just because it'll make it slightly easier, more precise with my measuring. And the distance over which that 400 meter change in elevation occurs is 160 meters. That's because on the ruler it's 16 millimeters, multiply that by 10, and it tells me that the horizontal distance over which that height change occurs is 160 meters. So using our conceptual triangle again, we can calculate the dip amount of that fault plane as the inverse tangent of the opposite over the adjacent. So inverse tangent of 400, which is the height change, divided by 160, which is the horizontal distance. And that tells us that the fault has a dip of 68 degrees. Okay, next question is asking us to construct a cross-section along that line of XY. So I take my strip of paper and I line it up between my bounding points, and then I mark on the ground contours first between the two extremes of my cross section to show everywhere that I go over one of these cardinal ground heights. So 1200, 1211, 1900, 807, then 700. Then I mark on the rocks on the surface, either with colours or labels. And then what I want to do is mark on the structural contours for the fault. So everywhere that I cross one of those structural contours, I've marked it on my cross-section strip. Okay, now that I've got all of that data, I can move over to my cross-section panel. And as ever, the first thing that I do is draw my hill profile by adding on all of the points that I've crossed one of my cardinal contours, and then drawing a hill profile line to go through those points. So I've got my hill profile sorted. Then what I can do to make myself feel better that I'm making progress, I can transfer from the strip onto my hill profile all of the points at which I cross a stratigraphic boundary, or boundary between two rock types. And then I want to transfer from the strip of paper onto the cross-section panel the structural contours for the fault plane, because that's the youngest thing on my map, so I might as well drop them on. I should really drop them on first. Okay, so all of these points here from my cross-section strip, I'm going to draw those the correct heights on my cross-section panel, and I can join them up to show where the fault goes in the subsurface, and then extend it to show where it would be with a dashed line in the above modern day erosional surface. Okay, at this point, in order to get the dips of the beds, I have to go back to the map and, yep, you guessed it, draw some structural contours. And because the contacts look conformable, you see how the boundary between the blue and the green and the pink, it's parallel here and here again. Then what I can do is just draw a single structural contour and everything will be parallel because it looks like a conformable layer cake sequence. So let's take the boundary between the pink and the green. I mark on all of the points where I know the height, wherever it crosses a ground contour, and then I mark on my structural contours by linking up those points of equal height. And I can see really nicely what this fault has done. Over on this side of the fault, the height of that contact is at 900, 1000, 1100, so we've got a dip direction from here in this direction. So if we were to continue this plane before we got to before the fault had happened, we'd go up to 1200, 1300, 1400 and so on. But you can see as we cross the fault plane, that same contact has been thrown down hundreds of meters, so that we've kind of been reset. We're back down to the 700, 800 meter elevations. But anyway, what we can do is get our cross-section strip back, whack that onto our cross-section again, and then mark on everywhere that we hit one of our structural contours for our beds. So I've marked on, here's where we cross the 1000, here's where we cross the 1100, and here's where we cross the 700. And then what I can do is transfer from the strip onto the cross-section panel those structural contours for the bedding plane. So here's my 1000, I plot a mark there, here's my 1100, I plot a mark there, and here's my 700. Okay, then what I can do is connect those points. So here it's really easy because I've got one at 1000, I've got one at 1100, so I can just draw a line through those. And then if I was a real sucker for punishment, I could go back and draw another set of structural contours for the contact between the green and the blue. But because I've had a look at the map and the contacts seem parallel to each other in map view, I'm just going to estimate that the other contacts that we see in the area, they're parallel to that one we've just drawn. Okay, then what I can do is add in some color to show the geology in the subsurface. And then what I can do is show that's what my cross-section is. Okay, this next question asks us to calculate what the apparent dip separation is along the fault. So the distance between two formally contiguous points along the fault. So this contact here between the blue unit and the green unit, before this fault had happened, can you see that they link back up? Like if this fault wasn't there, this part of the bed would just continue up like this, but it's been faulted downwards. So what we need to do is figure out first of all if the scale of our cross-section is the same as the map. And you can see that, yeah, 100 meters equals 10 millimeters, so 1 millimeter on our cross-section is equal to 10 meters in real life. That's the same scale as the map. So what we can do is measure two formally continuous points along that fault plane. So these 2 points, for example, they are 55 millimeters apart on our cross section. So we take that 55 millimeters, multiply it by 10, and it shows us that dip separation, the separation between 2 points along the dip of the fault plane, is 550 meters. Then the next question asks us to find out what the heave of the fault is, and that's the horizontal separation. So this is our dip separation between these 2 points, and the heave is that separation just in the horizontal dimension. Okay, so the distance between those 2 points in the horizontal dimension is 20 millimeters, which equals 200 meters when we multiply it by the scale factor. And then the throw, or the vertical separation, is the distance just along the vertical axis between two formally continuous points. So in the vertical axis between those 2 points, that distance is equal to 50 millimeters. So that 50 millimeters multiplied by the scale factor says that the throw in the fault is 200 meters. Okay, this next question asks us to figure out what sort of fault this is. Is it reverse? Is it normal? Is it strike slip? Well, we can rule out strike slip straight away. Well, for two reasons. One is that there's obviously dip slip has happened, so you know, strike slip, you only get strike slip, you don't get dip slip, hence the name. The other one, which is probably less strong but is nonetheless correct, this fault plane is dipping, and strike slip faults tend to be vertical. So we're left with deciding whether or not this is a reverse or a normal fault. And like I said in the lecture, imagine you sunk a mine shaft through this fault. Well, if you were stood in that mine shaft, then you can see that this block here towards X would be our footwall, that's where your feet are, and your little miner's lamp, you'd be hanging that on the hanging wall. Okay, so what we can see is, if we're using these terms in like footwall and hanging wall, we can see that the hanging wall has moved down relative to the footwall. Whenever you have a movement of the hanging wall down relative to the footwall, that is the sense of movement that describes, or that defines rather, normal faults. Okay, so the fault that we've got is a normal fault, and we've worked that out based on the dip of the fault plane and the relative movement of the hanging wall and the footwall. Okay, well, those are all of the questions. Feel free to pause this video as much as you need and come back to it and have a look around. If there's any questions, then catch me on email. But until we see each other next time, you guys have a good one. Thanks for listening.